Hello, calculus fans. Let's talk about the cross product in component form. Now, last section we talked about the dot product of A and B, and we defined it geometrically to be length of A, length of B, cosine theta. But then we went on to prove that if we had vectors A and B in component form, then we came up with this easy formula for the dot product. So this is a very easy algebraic method of computing the dot product. Now, we've seen a geometric definition of the cross product. Now we're going to come up with an algebraic formula for A cross B when we have vectors A and B in component form. This will allow us to not have to worry about what the angle is, what the normal vector is, what the right-hand rule tells us, anything like that. First, we'll write A and B using the IJK notation. Now we're going to use the distributive law to compute A cross B. So A cross B is A1I plus A2J plus A3K crossed with B1I plus B2J plus B3K. Now we're going to use the distributive law like a madman. So this is kind of like a giant foil. And when we do that, we get some horrendous looking expression like this. Now there are some nice things about this. I cross I, J cross J, and K cross K are 0, so those things disappear. And then we talked earlier about how to compute things like I cross J, I cross K, and so on. In fact, if we do that, we end up with a result that looks like this. A1B2K plus A1B3 times negative J plus A2B1 negative K, and so on. Now you should work out for yourself whether or not this really looks correct. Collecting like terms by I, J, and K, we get this. Now, this is kind of a horrible looking expression. It's technically accurate, but it's going to be too hard to remember. What we really need is a nicer way of computing this so that we can actually remember what's going on. So in order to find a more convenient way to remember it, we're going to use the concept of determinants. If you've taken linear algebra, you will certainly have seen determinants. A determinant of order 2 is defined like this. So basically it's a matrix. It looks like kind of absolute values. It's not really an absolute value. It's a different thing. It's a determinant. And it's computed AD minus BC. So for example, the determinant of the matrix 2, 3, negative 7, 5 is just 2 times 5 minus 3 times negative 7, and that works out to 31. A determinant of order 3 is a little more complicated to compute, but we can define them in terms of second-order determinants. So the determinant of the matrix A1, A2, A3, B1, B2, B3, C1, C2, C3 is computed like this. So we have A1 times the determinant of B2, B3, C2, C3 minus A2 times the determinant of B1, B3, C1, C3, and A3 times the determinant B1, B2, C1, C2. Let's see, so where do these come from? Like these coefficients, A1, A2, and A3, those are just along the top row. Now, where does A1 come from? A1 comes from here, and in that case, where does B2, B3, C2, C3 come from? It comes from here. A2 comes from here, and B1, B3, C1, C3 comes from here. Notice that that's what you get when you cross off A2 and everything in that row and column. Finally, we have A3, which comes from here. And then this determinant, B1, B2, C1, C2, comes from here. Again, by taking the original matrix, finding the A3, and crossing off the row and column that it's contained in. So notice that the coefficients on the determinants are the entries in the top row of the original determinant. So these guys here, the A1, A2, A3, show up here. So then the corresponding second order determinants are obtained by deleting the rows and columns from which the corresponding A sub I appears. Okay, so let's go over that again. Where, for instance, does this come from? Well, we take the A1, we go back over here, we find it here, and we delete that row and column, and then what's left over is this determinant here. And the final thing to really make sure you take note of, it's very easy to forget, is this minus sign here. One of the most common mistakes is forgetting this minus sign. Okay, let's run through an example of computing a third order determinant. First thing to do is to expand this into 3 separate order 2 determinants. So you can see that we're expanding across the 3, 2, negative 1 in the top row here, and that turns into this 3, the 2, and the negative 1. Also, don't forget about this minus sign that we just have to throw in the middle term. Then we have to work out each separate order 2 determinant. Those are easy to calculate. And when it all gets boiled down, we get a determinant of negative 17. So now, let's take our formula that we previously came up with, this horrible looking expression for the cross product of A and B. Now this formula is technically correct, but not very easy to remember. We'll write it with determinants. You see now, A cross B can be written this way. Check that this is the same thing as what we had before. And now what you should notice is the similarity of this formula with the general formula of a third order determinant. Now we can write a nice formula for the cross product of A and B using a third order determinant where we throw in ij's and k's, and it looks like this. So this is going to be the way that we're going to compute cross products. We have to do it with a third order determinant. And if you understand the general procedure of how to do that, then it's very easy to compute these determinants. It definitely takes longer than computing a dot product, but it's not that hard to do. Okay, that's all for now.